Well, good afternoon, everyone. My name is Jared Leake. I'm the CEO for the Australian Alliance for Energy Productivity, or A2EP as we're better known as. And I'd like to welcome you all to our webinar this afternoon. It's a follow-up from our previous heat pump webinar done last month. Today we're talking about selection of heat pumps. First of all, I'd like to start this webinar by acknowledging the traditional owners where I am living and broadcasting from in the northern suburbs of Sydney, that being the Darramurrugal people, and I pay my respects to their elders past, present and emerging. And for those of you that are new to A2EP, we're a non-for-profit organisation. We are funded by our members, and there's our members right there. And these members also share our mission of doubling Australia's energy productivity. In short, energy productivity means more dollars from less megajoules, and we help drive the transformational change to make this happen. A2EP is all about taking roadmaps and reports and making them reality. And we like to see energy productivity in action, or EP in action. And that's what we're all about today. We're going to be seeing great EP technologies like heat pumps become a reality, and this webinar is part of a larger body of work that we've done with ARENA on using renewable energy to power process heating. And this is seeing many more heat pump projects and process heating projects go ahead using renewable energy. Today, joining us, we have Peter Henke from ARENA. Welcome, Peter. You'll be joining us for the introduction discussion. We also have Rob Nicholson and Charles Luo from pitt&sherry to present there on the heat pump selection guide, along with Derek Harbison and Manuel Siegrist coming from SmartConsult. Welcome to you all, and I'll open the floor to you all in a minute, and we'll have some further introductions as we get going. For this webinar format, please add your questions in the Q&A box you'll see at the bottom. So if you type in your questions there, and any questions you like, you can upvote them, then we'll certainly get to those questions as we go through the webinar. Later in the session, we want to try and make it really interactive with the tool that we've developed. So we look forward to your comments in the questions or in the chat there for some scenarios that we run through with the tool. And certainly with this tool today and the webinar, we're really hoping this is going to make it a lot easier for you to select, design and integrate a heat pump into your process. As I mentioned before, this presentation will be recorded and distributed sometime early next week, along with contact details of our speakers, so you can get in touch with them if you want some further information as well. The tool that we're developing, as is sponsored by ARENA as well as Mayekawa and AMPC. I'll say that the tool and the work that we've done, it is a work in progress. I'd like to think we're at a sort of an 80% level, and it will require some further work, and that's what we're hoping to achieve out of today, is having some further feedback from yourself to get that to a higher level of readiness to further roll out. Can you ever get a tool like this to be perfect for everybody? No, but I'm really hopeful that after this session, you'll see what's coming and you'll give us some feedback to make this even better for when this is launched and finalized later this month. Very good. With that, I'll just start up a presentation here and let you know what's happening in the world of heat pumps. The technology investment roadmap, some of you may be aware that the targets or focus technologies were coming out from the government last week. Heat pumps was not one of them. Other things like hydrogen, soil carbon, carbon capture and storage, and batteries and what have you made that top 5. I understand this list will be updated every year. I'm still somewhat hopeful that heat pumps might make it there in a future year of this technology investment roadmap. You'll see it is one of the best technologies already identified at the bottom left of that bubble chart there, giving a really good potential for CO2 reduction and at a negative cost per tonne. Therefore, it's a profitable decision to be investing in heat pumps. One thing to notice with the existing heat technology roadmap there is that purple bubble is only for commercial buildings. The federal government hasn't been really looking at this at an industrial scale just yet, and certainly we're on a track to try and help them to look at that more on an industrial scale. Peter from Arena's here. Peter, Arena's been doing a lot of work with energy usage for process heating and mapped out a lot of where the heat flows and everything are going. Maybe you could take us through some of this charts there from some of the reports that you guys have done.
Sure. Thanks, Jared. Yes, this slide that you've got up at the moment is a shot taken from a report that Arena released about a year ago now, towards the end of last year, called Renewable Energy Options for Industrial Process Heat. Bit of a mouthful of a title, but it's a really great compendium, I think, of sort of covers all sectors, all process heat requirements, and all energy types, and gives a good overview of where process heat is used in industry, and what the renewable energy options might be to address that. So you can see the graphics sort of coming in here, that the big picture is industry takes up about accounts for about 44% of total final energy use across the economy. So buildings and transport are the other two major chunks there. Then of that 44%, roughly half of it, just over half, is fuel for heat. And so that's mostly natural gas and coal, of course. A little bit of bioenergy is in there, and some other fuels like LPG and other fuels like that. All of those things go into providing process heat for industry, and you can see the segment over on the right hand side there sort of breaks that up into different temperature groups, and you can see that right down the bottom there, there's just a bit under 10% of it is used at fairly low temperature, below 150, and in fact a large chunk of that is actually below 100, so just hot water, that kind of thing. And then progressively, as you go up around the arc there, more energy getting used at higher temperatures. But really the point of putting that slide up is the focus of heat pumps at the moment is in that below 150 or even below 100 right at the moment is the sweet spot for heat pumps. There is work going on to sort of push the operating envelope of heat pumps up to that 150 and even well beyond that, but that's a little bit further down the track. The here and now is the below 100 sort of space. So that just sort of gives you an overall picture, and as I say, that's kind of the sweet spot for where heat pumps are operating at the moment. And just quickly, that's the graphic of the report there. So I'd recommend that to anybody who hasn't had an opportunity to have a look at it yet. It's on our website, the arena.gov.au website. And yeah, certainly recommend it to you. It's broken up by industry sector and also technology type. Back to you, Jared.
Yeah, thanks, Peter. That report really goes through your options as well. Biogas heating, hydrogen, geothermal, and other electric sources as well, like pulsed electric field or ohmic and things like that. So yeah, it's a really good resource for anyone who's thinking about this decarbonising that process heating. There's one other comment to make there is those temperatures in that green section there, that's the temperature that is produced, say, from the boiler. The boiler might be producing, say, 150 degree steam. It's not the end use temperature, like for pasteurization, which might be like, say, 77 degrees or so. So further work is actually going to be done on that with this Race for 2030 CRC, further research to find those the usage of that heat much more.
Yeah, that's a really important point, Jared. I should have pointed that out, that yeah, a lot of that information just isn't readily available to put into a report like that at the moment. We just don't have the end use data that enables that breakup. So yeah, conceptually some of that stuff in the 150 up category might actually be energy use that's appropriate for a heat pump. It's just that the steam's being generated at 160, say, so it goes in that higher group, but then the steam ultimately produces hot water at 85 degrees or something. So yeah, there's a lot of applications like that.
And further from the report on the chart on the right hand side, the Arena report broke that down into different segments and what have you, and you see a large amount of low temperature heating for food and beverage, as well as commercial and services, and a little bit there for petroleum refining as well. I mean, I just took a simple calculation. I said that 9% of that of all of that heating below 150 degrees, that gives you about 65 petajoules of energy required, of heating required. If I said, you know, an average of utilization for a boiler slash heat pump might be say 50%, that would require about 4 gigawatts of installed capacity of heat pumps and an investment back of the envelope of about $2 billion. That's just using some data from A2EPs gained from these heat pump sort of studies that we've been doing over the last couple of years. That number itself needs more work and more definition around it. But one thing's for sure, it is not a small amount of money that's expected to be heading towards heat pumps as we see them gaining more traction. If we just look at a few of the drivers for heat pumps, you know, the biggest driver for any sort of energy productivity is having net zero commitments. And we're seeing more and more companies making that. We've got Lion is one of the latest that have made commitments to net zero, and with that flows on a lot of necessary investments to decarbonise what they're doing. And certainly for using heat pumps below 100 degrees, it's absolutely here and now, and we'll see that today. That little graphic I've got there on the right there, that's from ClimateWorks, and they've got their net zero momentum tracker. So they're keeping an eye on companies and trying to help with reporting on who is committed to net zero emissions. Another driver there for heat pumps to mention is that electricity prices. I assume a lot of energy users and energy managers have been seeing the contract rates coming out for electricity for next year. And certainly the rates that I've seen around are, wow, they really are coming down. For electricity. For gas, still a lot of uncertainty. If you join our energy users webinar where we have Tennant Reed from AI Group join us, you know, his picture is still a lot of uncertainty for gas, and certainly the prices for gas don't seem to be coming down near as much as what they are for electricity. That differential is certainly driving more towards the use of heat pumps as well. Another interesting fact for the heat pumps, you know, you can store a lot more heat energy compared to when you're using steam and natural gas. There's just no value in that, but you never see natural gas go to a negative price like it is now for electricity prices. So it's really a huge opportunity for those that want to store energy, store thermal energy in, say, a thermal battery, which is a large tank of hot water or very cold glycol. So this is can reward companies for that negative electricity price. Got a couple of examples here for you before we get into some specific studies from that Rob from Pitt&sherry will give to us. Here's an example of abattoirs. Like, you know, if we say there's well and truly over 100, there's about 120, 130 abattoirs around Australia. If you were to say that these were retrofitted with heat pumps to use for the washdown water and the sterilisation water, I mean, there's a potential saving of some 1.6 million gigajoules per annum of gas usage. Just an enormous number. You can multiply that times your usual price per gigajoule for gas, and you'll see there's a huge quantities, huge amounts of money available we're talking about here. Dairy farms as well, whilst dairy farms, their individual sites don't have a big load of gas or heating demand. There's, you know, nearly 6,000 farms out there all having to produce hot water for their washdowns and cleans and sterilizations each day. You know, you add that up and how much water they need to produce, and it's some 300,000 gigajoules per annum. Finally, if you look at, say, aquatic centres, you know, if you look at, say, the top 300 or so aquatic centres and look at the typical loads of heat that they have, if you were to add all of them up, you're looking at some 500,000 gigajoules per annum usage of natural gas. And with more and more councils committing to say, hey, we want to decarbonise, we want to go past just using 100% renewable energy, we actually want to decarbonise as well. Well, heat pumps is absolutely the most viable alternative to do that for aquatic centres, and the huge amount of potential energy savings there as well. Rob, we've got from Pitt&sherry on the line. Rob, your company's been doing a lot of various studies on the usage of heat pumps. I was hoping you could share us a few cases of where this is happening right now.
Yeah, sure. Thanks, Jared. as part of the A2EP arena studies over the last couple of years, we've looked at a number of industries specifically, and there won't be specific sites I'll talk about because I know that when we go through the selection guide that examples will be used. But we found in brewing, particularly large brewers, well, they don't have to be large. The sites that we use were large brewers. Where there's a source of a good source of heating or demand for heating and cooling at the same time. One of the changes we see specifically in that industry, I guess, is their working demands are changing, and so rather than producing a large amount necessarily of one particular product, they're diversifying and producing smaller amounts of a much broader range of product or brands, or still might be brewing the same product, same beer, but the same type of product, but different brands changing over. Boiler efficiency or boiler utilization was then really becoming an issue insofar as its effectiveness or its efficiency. And you mentioned before about just the boiler utilization. If the lower it becomes, the greater the opportunity there is for a heat pump. And we found that providing heat on demand where it's needed, whether it be for cleaning in place or whether it be for pasteurization, presented a good business case to look at those sorts of things. Very much in that temperature range that you were talking about, sort of the 65 to sort of 75 degree range, where boilers are producing much higher heat but having to then distribute that heat over longer distances. Heat pumps work well in there. We also looked at frozen food production, frozen vegetable production, and a range of different things, and extracting heat from different sources, from sewer sources within those facilities. Drying in confectionery was another one that one of the earlier studies that was looked at, and that's a different use for the heat pump, but also proven to be effective. Even things like if you go further up the supply chain from, say, the brewing industry was hops production. Now, hops production was a challenge because of a really, really short window of processing. But, if you can combine that sort of use with other uses in other industries, then you've got a good case for heat pump utilization. And you mentioned before in the meat processing area, it's not a new technology per se, but businesses are having to adapt to their different production needs. They're having to adapt to different, customer demands, different products that they're producing. And this is really part of a transition in manufacturing for process heat that allows businesses to say, I can do this much more productively and not have, redundancy built into a boiler running all the time when I don't need it running all the time. I think the big play out of this as well is the ability to use renewable energy to provide the electricity to run the heat pumps. So while the electricity prices are going down, renewable energy prices are very low, and they'll continue to fall. And whether that's using just the energy that's produced, and depending on your utilization factors of your equipment, or generating behind the meter renewable energy, storing it and then using it, or doing the power purchase agreements for larger sites. You can electrify your process, have it used much more effectively, much more productively, capture that waste heat that's coming off a cooling process, reuse and preheat your heating processes. Those are the sorts of things that we applied, that pinch analysis to this process. We were allowed, we were able then to identify what are the areas that businesses can really start capturing some of that waste heat, using some of that cooling, and then incorporate that into their process much more productively. And I think, we've only just sort of hit the tip of the iceberg in this, and that study that was issued last year, together with that document that was issued last year, together with the studies that have been happening it really has an opportunity here to change the industry quite significantly, and I think, and give people energy security, energy productivity, and certainty with, backing it up with renewables. It gives them certainty of price as well.
Yeah, thanks, Rob. There's a lot of factors coming together to say, hey, this is becoming a smarter and smarter decision. Just want to pick up on one thing you said there about boiler efficiency, and just one comment there, and this is more, I guess, from previous and other presentations, but boiler efficiency, people will usually say, yeah, my boiler runs well, it's got an 86% efficiency because I've got an economizer on there. Okay, that's the boiler itself. But certainly we've seen the studies which say when you consider the entire system and the other heat losses through that steam system, it's typically going to be well below 70%, sometimes down to 30% because of the poor utilization of the boiler. But that boiler, very rarely would you say the entire system is going to be above 75%. That's for sure.
No, that's right. And I think, as I go through the selection guide this afternoon, by changing some of those parameters, and if we know that, even the default one, if we use it 80%, coming through with some of the resulting numbers, the more information that you know about what's happening on your site, and this is really an important part of the process, that this selection guide will give you a really good prompt to say, what, I need to look into this a bit further, and then doing some of that initial sort of pre-feasibility, that investigation, understanding your data and your thermal loads within the site will make an incredible difference, and it will really open up what co-benefits there are to go along, just besides the energy benefit and the energy resourcing benefit. Thanks,
Robin. And metering and monitoring, getting that data, that's our next Thursday's webinar, but thank you. If we talk about making a case for heat pumps, so we saw that with ARENA, we worked through about 20 different studies for process heating. I believe it was around about 70–80% of those actually looked at heat pumps. The others were looking at biogas and solar thermal and things. And when we look at the heat pumps, there's so many questions came up, and we noticed the various consultants and end users ended up with a lot of questions. And this shows us sort of the supply chain and the understanding of the technology. It's not 100%. We're all not there yet, I'd suggest. And there's a lot of questions here that need to be answered. And look, this selection guide that we're going to go through, I'm very hopeful this will take us a long way to helping you answer those questions. There we go. There was, just before I hand over, there was one thing I want to talk about, and that's the return on investment and some sensitivity. We'll see, we'll work through that today. But one thing that we had was very clear on that, the sensitivity on return on investment for a heat pump was gas and electricity price. That was number one. We saw the steepest part of the curve there for sure. The other part was that coefficient of performance and how do you maximize that, and yeah, we'll talk about that today, and just want to pick up on something that Rob said before. I hope you all picked up on it when he said recovering heat from sewer waste. And that's the sort of thing that really can flip the equation here in return on investment. If you start thinking that's absolutely thinking outside the box. It has been done before. A company out of Canada, I think it's called Shark. They're doing this already and using that. And I think it's maybe in the Christchurch airport there. It's being done. But yeah, this is the sort of thinking you need to have, is thinking outside the box of where can I have that heat source coming from. Good. With that, I'd like to hand over to the two gentlemen who've been working on this heat pump selection guide. That's Charles Luo from pitt&sherry and Manuel Siegrist from SmartConsult. Derek Harbison's also been in there consulting on this as well. I'd like to hand it over to them to take us through the selection guide and how that's come about and where we're at with that right now. I'll stop sharing, guys, and hand that over to yourselves, and we'll go.
Perfect. Thank you so much, Jared and Robert. Welcome everyone, and thank you for your attendance. Would like to talk a little bit about our heat pump technology selection and selector. A quick overview, we'd like to talk about the purpose. Why are we doing this? We've already heard a few ideas around why we want to do this and how this could be useful for your business. We're going to go very briefly over the glossary and then get into the heat pump technology selector. What are the deliverables? What do we want to demonstrate? And show a few case studies, how the calculator can be applied and what sort of outcome can be achieved with it. Now, I'd really like to stress this, that we do need your input. We need the input of the audience. This is a work in progress, and we very much look forward to refining it. As Jared mentioned before, this is a 80-20 sort of stage, so we very much look forward to refining it with your inputs. Now, with regards to the purpose, what we're trying to provide is an easily accessible pre-selector of heat pumps. It should allow the decision makers to navigate some of the key decisions around the heat pumps, even if you don't have that much knowledge in that topic yet. And for that purpose, it should be a resource of in-depth information and also industry contacts where you then can investigate heat pumps further. It should also serve as a general promoter of heat pumps and showcase and highlight their usefulness. It is an investigative tool, right? So we have to make sure what it is not. It is not here to give an absolutely accurate cost estimate and also not a definite solution to your answer. And it cannot replace a good engineering investigation on site, but it should give sort of at a first glance an idea what the purpose of heat pumps could be in your business. And as Robert mentioned before, the better your input, the more exact the output of this heat pump selector will be. On the glossary, I would just like to talk briefly about the heat source and the heat sink, and the rest is sort of for your own edification if you'd like to go through the presentation at a later stage. So heat source is the thermal energy reservoir where you get the heat from, can be the air, ground, or the water. And the heat sink is the heat supply that you're producing. So what are you trying to heat up? This is sort of the two terms that we would like to highlight. With regards to the deliverables, I'm just going to hand over to Derek, who's conveniently sitting next to me.
Thanks, Manuel. Can you see the next slide? So let's talk for starters about what are heat pumps capable of. We're surrounded by heat pumps. We have heat pumps in cars as air conditioning systems. We have heat pumps in refrigerators. We have heat pumps in larger scale, for instance, chillers that are used. Some of the universities in Australia have university-wide cooling systems or chilling systems. RMIT has a heating system at the moment. They're looking at transferring over to a district heating system using heat pumps. On the Gold Coast, we have Bond University, which for 25 years has had a chilled air conditioning system that's been in existence across all their buildings. And these are heat pumps on a very large scale. But going back to basics on heat pumps, this is technology that's been around a long time. In the 1850s, James Harrison investigated the first, or not the first usage, I've got to be very careful here, he investigated the first commercial scale efforts at using heat pumps at making ice of all things, because of course in the 1850s keeping things cool was very difficult unless you're using evaporative air conditioning, or sorry, evaporative machines. So he not only established the worth of these machines, but then went to England and started selling them at trade fairs over there, which was, you know, a huge amount of forethought. Going on to the actual machines themselves, if we're looking at the process there, we call it the vapor compression cycle, and we have an expansion valve, a compressor you'll see at the top of the diagram on the left, an evaporator and a condenser, and every heat pump that you see will be a variation of that process and that design. On the right hand side, we just put some examples in today, and Jared sort of looked at one of the diagrams we had and he queried that, and it's quite an important point. On a two-pipe system for a heat pump, we have fans on the top of the unit, and basically cool water is going in and warm water is leaving the machine, and cold air is being rejected from the top of the unit. Now this machine is for heating water. On the right-hand side, we have a 4-pipe system. We have a cool loop that's going in where cool water goes in and then cold water comes out on the second pipe. And then on the right-hand side, we have a second loop, which gives us warm water going in and hot or warm water coming out. Now, this is an important point to consider, because when we have a hot or a cold and a warm side of the heat pump, we can use the heat pump for cooling, heating, or for heating and cooling simultaneously. And this is a very important point with a couple of other slides we come to in a moment. So where can we use them? Well, all sorts of industries can use them, and some industries at the moment haven't realised that they can use them. For instance, in the cooking area, if I want to heat up water, for instance, for a canning process, and we heat up the water, you know, we can, for instance, some tomatoes, and we put them in, and we want to increase the temperature of that. We can use a heat pump for that. When we go over to wood products in that area, then things get a bit more interesting. In that area at the moment, we're drying and we have humidification, or actually dehumidification. We want to take moisture out of that timber, for instance, and we want to dry out that timber. So the heat pump there can be used to cool. The cold side can be used to reduce the moisture of the air, and then we also can use the heat from the heat pump to then raise the temperature of that timber. For instance, normally they'd have it in a timber dryer, a long timber dryer, and they usually use steam and all sorts of things, all sorts of processes there. The same process can be now managed by a heat pump more efficiently. And then also we have, actually we'll leave it at that one. And Manuel, if we can go to the next one. So what does the design look like? Well, again, as Robert was pointing out, you need to step through and establish some data around the unit. For instance, we have to understand how we're going to be using heat or cold from the unit, or hot and cold. And we need numbers around that before we go too much further down the track. Now, the sizing of the equipment, this can be a difficult one. Coming from a gas world into a heat pump world, the numbers may not match up as you would expect. Jared before was talking about the use of thermal storage, and this can be a little hard to get your head around, but if I turn on a hot water service at home and I turn on the shower and I get instantaneous hot water, a heat pump doesn't approach things in that way usually. It's a longer period of time that I'm taking in the heat from the atmosphere and putting it into my water storage unit, and I might hold that to a point where it's more beneficial to be using the hot water at a different time of the day. And this is particularly pertinent when solar systems come into play. We may make warm water or hot water during the day and then use it at another time of the day when electricity is more expensive. So it's a game that we can start to play now by shifting. Again, we're transferring heat with heat pumps and using that at different times of the day depending on the energy system. The floor space that we're using for the heat pump may also not fit in with our expectations. If we're putting a heat pump versus a gas system pound for pound, it won't be possible to make that comparison directly, because there are other elements of different heat pump systems that take up more space. Some are compact, where we say they are packaged units, and some are spread over large areas, which might be, some elements may be 60 metres apart. So it's difficult to make a comparison there, but it has to be carefully considered again. You can't just assume you're going to drop a heat pump into where a gas system was. Thermal storage, last one. Thermal storage is cheap. Water is the most efficient way of storing energy on the Australian market at present. You'll see some people putting forward phase change materials, which is essentially a variation on the theme, but water, pound for pound, is cheap. And when we put it into just tanks for storage, it becomes, it's a thermal battery, and it becomes a very efficient way of holding energy for using later in the day. So I just have to explain this bit just briefly. If we are talking about the inlet temperature of the heat pump, and we're talking, say, a target temperature of 50 degrees that we're aiming for, heat at 12 degrees, for instance, on the low side, the cool side of the heat pump, can be valuable to you. So again, coming from a gas side, we're looking for an output, say, at 50 or 70 degrees, and you're not really fussed by what the temperature of the water coming into the gas system is, but you are with a heat pump. All right, so what are the decision drivers in selecting a heat pump? We've just gone through on the last slide about whether we're wanting heating, cooling, or both required. We need to look at the thermal capacity requirements, and those numbers have to be thoroughly understood. Then we have to look at the temperature lift. That's the starting point of what our heat source is to what our target temperature is, what our heat sink will end up being. And we may have different heat source availability. Now, because we're talking about lower inlet temperatures or inlet temperatures which may be different from our target temperature, a river or a dam or a ground, or the ground where you can take heat out of the ground for ground source heat pumps, or a mechanical process. If you're in a factory and you have steam being given off, lunchtime today we're talking to an installation in Geelong where they have a flame next door to their heat pump that putting in that burns 24/7 at 700 degrees, that's 2 meters high. So you can take heat from that flame and input it into the heat pump to provide a boost to all the heating across the building. Business location, heat pumps work more efficiently if we're heating in a warmer climate than they do in a cool climate, but that doesn't mean they won't be viable. Again, we have to wade through those numbers very carefully to work out the business case for installing them. And as Jared pointed out before, the cost of energy in all of these equations, you just cannot assume that heat pumps are a magic bullet and they will be more efficient than gas. It comes down to the cost of the energy, the space we have available, and also the efficiency of the heat pump.
Wonderful. So with regards to the costs, it is a really good segue into some of the consideration that we want to make when it comes to the return on investment, and also some of the errors that we try to prevent. So as it was mentioned before, heat pumps work vastly different than a gas boiler, and their efficiency, so their coefficient of performance, is very, very different. Therefore, we do not size for the peak loads, but more for the average usage. Therefore, we can prevent unnecessary capex, so initial outlay of capital, and of course also the underutilization of the heat pump. One of the things that we need to consider for the return on investment is some basic financial modeling. While there can be an initially higher capex, this will be offset by a subsequent lower operational costs and OPEX. Right? So it is really important to understand your business and what the usage would be to optimally size the heat pumps so that they can work most efficiently. But also, as mentioned before, so Jared was talking about sewage heat recovery, for example. That's not the only way that you could recover heat, but it might be a way. Derek was just talking about using a next door neighbor that has some sort of a heat available. This can be all integrated into that system. And this really speaks to the last point for system integration. Because heat pumps are running with electricity, they can, for example, integrate PV, solar system. Robert was just talking about how the price has increases to come, or keeps on coming down. So this provides a great opportunity to further drive down your operational costs. Some of the other considerations that need to be taken into, that need to be factored in, some of which we've already talked about. So is it a greenfield site? Is it a retrofit? Retrofits are in general a bit more complicated, a bit more complex, can be more costly. It all depends. It's a case-by-case basis. But this just needs to be taken into consideration. For a greenfield site, much easier because the design can be accounted for that purpose. Now, since heat pumps do run on electricity versus gas, it needs to be made sure that there's sufficient electrical capacity on site. Is there a low-grade heat accessible somewhere? Because this can further drive the efficiency of the heat pumps. Now, depending on where your business might be in Australia, where it is located, it might be very important to select the right equipment because there might not be service capabilities where you're located. Plus, depending on the type of heat pump that is chosen, it needs to be made sure that the safety requirements and safety standards are adhered to. Now, aside from the energy benefits, because we have now talked a few times about the efficiency of the heat pumps, which then results in a direct lower usage of energy compared to other systems. There's also other benefits that we should talk about. For example, environmental. As we mentioned, they run on electricity. Therefore, it is possible to run them CO2 neutral, depending on where you get your electricity from, be it from your solar system or from a renewable grid. Now, the service and maintenance cost. Here it is just the predictability of the maintenance costs, and they're possibly lower or potentially lower than a comparable gas system. Whereas with the longevity, there are cases of heat pumps in Australia that have run for 30 to 40 years. So we do have some great case studies there about their reliability. In our selector, we specifically look at refrigerants that are natural. So they have an extremely low global warming potential or even zero global warming potential, which makes them very future-proof. Because as some of you might know, some of the refrigerant that is very commonly used in air conditioning units, for example, is being phased down in Australia and will become increasingly unaffordable in the future. So this would be really a future-proof solution from that point of view. Now, in combination with all the system integration, potential use of PV solar, and the efficiency of heat pumps, that means you will most likely end up with lower costs of production and as well as localized heat production on site. Now, I know this was a lot of talk. That's why I would really like to hand over to Charles now, who's going to run us through the selection tool and actually see this a little bit in action. So Charles, I will hand over to you.
Yep, no worries. Thanks, Manuel.
Great.
Let me just share my screen. Perfect. So for the next couple of minutes, I'll take you through the use of this selection tool. Our goal, as I said previous, was to incorporate all the factors that we've just described into either this tool numerically or into a series of talking points that will come up as you use the tool. One of the biggest challenges with using heat pump technology to replace process heating is the complicated nature of a heat pump's operation. And there's often more than 2 thermal streams, all of which are physically separated. And the thinking around heat pump design also differs a lot from traditional boiler design, where the focus has always been to provide peak heating loads. Instead, we're looking at providing average loads and then use thermal storage to accommodate peak demand. So before I move on to the actual tool itself, I just want to re-emphasize the 2 most critical terms because the calculator refers to them a lot, and that's the heat source and the heat sink. Simplistically, heat source is where we're getting the heat from, and you can see the purple arrow coming in, that's where the heat is coming from. The heat pump upgrades it, deposits that heat into the heat sink, which is hot water or hot air, and that gets applied to the site. So I've got a set of test parameters just to demonstrate how the heat pump works. So I'm just going to exit the presentation and go straight to the, oh, there we go, the calculator here. So do you see that, or do you still see the screen for the presentation? Yep, excellent. So you see the spreadsheet. So we have a set of parameters in a hypothetical site. In this case, it's a factory. It's got a natural gas boiler producing 80-degree water for a single process, which could be preheating of plastics before it enters the injector molding, for example. The process is relatively continuous, and the engineers estimate about 6,000 hours of use per year. The average heating load for this process is about 350 kilowatts. The peak boiler load that it currently has is 500 kilowatts. The site also operates as a cooling process, which requires a stream of 10-degree water to be used. So this could be cooling the plastic after it's been molded. And the cooling, once the cooling is done, the water returns to the ammonia chiller for regeneration at 30 degrees Celsius. So it goes from 10 degrees to 30 and then back to 10 by the ammonia chiller it's got. So the site's in Brisbane. It's got a marginal energy cost of $12 per gigajoule for gas and 10 cents per kilowatt hour for electricity. So what I'll do is actually enter these parameters in there and see what the results are. So we have $12. There's no process heating cost. We know 6,000 hours of use. So I'll go relatively quickly. And the reason I'm using average heat here is the fact that heat pumps requires storage to make it feasible. And this tool has an implicit assumption that storage will be installed, and that's factored in as a rough factor in the CapEx. So you'll see that come through. We'll never use peak heating for heat pump size unless that peak heating is the average heat required. So the heat source in this instance is water. It's that cooling water that the process use. The location is in Brisbane. Now the location informs, doesn't make too much of a difference on the calculation if it's water, but it does if it's groundwater or ambient air, because the temperatures change fairly dramatically between different cities. So the heat source in, so that's the cooling temperature, is 30 degrees. That's where we're extracting the heat from. We want 80-degree water to come out. Is cooling usable? Yes, we want to use the cooling. And the cooled water temperature after it's gone through the heat pump is at 10 degrees. So straight away, we can see some rough paybacks, some rough savings that are calculated, including the maintenance and energy cost of the heat pumps, as well as some rough CapEx of the heat pump system and the size of the heat pump system required. We've got COPs of the two refrigerants based on these temperature ranges that we're working on. And this allows you to immediately, within 5 minutes, look at whether this is worth considering. And you can play around with these figures. So right now, we've got no cost of maintenance for the boiler. If we do know the cost of maintenance, so here there's a set of advanced inputs that you can actually use in the tool that are optional. Now, these are for more advanced users of the tool. So it might be your systems engineers or your thermal engineers on site. If they know the operating cost of the current system, so if the boiler requires around $6,500 to maintain, which is fairly low for a relatively old 350 kilowatt boiler, we can see that the equation changes quite a lot. So looking at this tool, you'll probably look at ammonia as a start because it's got fairly low CapEx and good savings. CO2 can do the job as well. It's fairly close and the savings are similar, but the cost of CO2 systems is typically higher at the moment. And you can add to this the use of solar power. So if I were to say I'll have a PPA which supplies 40% of this heat pump's energy use with solar power. Solar power is far cheaper than the site's current electricity cost. You can see the payback dropped from 5 years and 5.5 to 4.6 to 5.2. And the whole purpose of this tool here is just for you to play around with your figures. What works on your site? What's your current circumstances? And give you some rough numbers. So I'll run through a second example as well. I've got three.
There, Charles, maybe I'll kick things off and give some ideas of how some people might like to write in chat there of some suggested changes or see how the tool handles it. You know, you could say, for instance, look, I'm thinking of putting in solar PV, and therefore I've only got solar. You know, I've only got that for say 12 hours a day. Therefore, I may need to double that average heat required to 700 kilowatts. But yet, you know, that means the electricity price is going to come down maybe to half of that. You can pretty quickly simulate that there as well, yeah?
Very easy. So if I double the heat, but now all of the energy is from solar, then we can see what happens. So the cost of gas and electricity, as I said previously, are big determinants in what this payback looks like and what the savings are, because it's all around energy use. We can model that, and this tool allows you to quickly sort of understand what that might look like for you. Is it worth it to actually look at more than doubling your CapEx to reduce the payback because you've got more solar utilization? That's a question that this tool can answer fairly quickly. And I did see some questions in the chat, so I might just divert from my presentation slightly and answer some of them now. So one person asked, what are the applications of heat pumps in aquatic centers? Well, we can look at it here. In an aquatic center, you're heating the water. So let's say the process use for the water heating is about 4,000 hours a year. So that's roughly 10 hours per day, 365 days a year. We'll leave the energy cost as is. We'll leave the average heating as is as well, because it could be any size of the pool. And we'll leave it as water in Brisbane. the heat source in temperature. So where can we extract heat from in an aquatic center? So you might be taking it from the chilled water loop for your HVAC, for example. So that will come in at say 20 degrees, and you want the water temperature going into the pool to be about 50, let's say, to mix it with the makeup water to turn into the temperature you want. And the chilled water from the HVAC system will be about 6 degrees at its coldest. So let's ignore all this for now. And you can straight away see in an aquatic center, you wouldn't go with CO2. That is the wrong refrigerant to use for these sort of temperatures. An ammonia system would give you fairly good payback if you just straight up replace an old school boiler system, because it can supplement that cooling for your HVAC. So that cooling could be used to dehumidify the pool, for example. So that's one application.
With this one, Charles, you could say, well, I could change my heat exchanger setup potentially, and maybe my flow rate and return rates, and instead of needing 50 degrees, maybe I just want to take that to 45. You can quickly see maybe what does that impact on that on the COP as well. Looks like the COP may have maxed out there, and it's not going up much further, but I think it's still
I think this is as good as it can do for ammonia. So even if I go to 40, it's not going to change much. There's a theoretical limit that we've put in just to be a bit conservative. But it is feasible for COPs of 6 with low temperature lift. So this is a fairly low temperature lift from a heat source temperature of 20 to a heat sink out temperature of 40. And this is a dream scenario for a lot of ammonia heat pumps. So I'll move on to the next one. So we spoke about the opportunities around abattoirs. So here's a hypothetical site. It's an abattoir. So it's got a natural gas boiler and it's used to produce steam. And part of that steam is for a CIP system, a clean in place system. 85-degree water is needed at an average heating load of 1.2 megawatts. So it's a big system, a big CIP system. It's used for 6 hours per day at 200 days a year. So they're fairly low utilization. And there are nearby large cool room that requires chilled glycol at -6 degrees and then return glycol temperature of 4 degrees. But there's additional points here where the steam boiler is a long way away. And the engineers on site have found that the water heating system is about 45% efficient from steam because of that large transmission losses. The site's in Adelaide, so the energy costs are rather high. Now we want to know, right, is this application worthy of considering heat pumps given the very low utilization of the heating process? So let's find out. So I will, again, quickly put this in. So it's used 1,200 hours, 200 hours, 6 hours a day, 200 days a year, 0.22 as electricity costs. That's the heat. We want water. And we want the site to be in Adelaide from 4 degrees to 85 degrees and -6 degrees as the glycol out temperature. But here we know that the current system efficiency is only 45%. The default for this is assuming everything's a natural gas boiler, so that's about 80%. If you're looking at LPG boilers and LPG replacement scenarios, which one of the questions did ask about, you would adjust the fuel cost to your LPG equivalent and your heating efficiency to an LPG boiler, which is about 70% max, and that's the only thing you'll change. So in this scenario, even with the low utilization, heat pumps would work fairly well. And in this temperature range, both heat pumps perform similarly. Now, carbon dioxide as a refrigerant performs better in the sense that it produces more savings and larger energy savings, but that's got larger capex. So you can then decide, all right, do I need to look at this ammonia or do I look at carbon dioxide? Maybe you later on do a more detailed thermal audit and found that this is actually only 30% efficient. Again, you can see the effects on the business case straight away. And a lot of these is designed so you can add things in as you find out. So maybe if the boiler you're finding it has a maintenance budget of about $12,500. Now, not all of this is for the steam CIP system, but let's assume it is for now. And again, that has an effect that's taken into account in these calculations. It's important to note that the CapEx that we've put in, we've based on real projects that we've done and A2EP has done over the last 12 months. They're fairly conservative in the sense that they account for a lot of site difficulties that we've encountered. So we expect that to be on the high side, which is why we've put in about 5% over, about 20% under for a lot of ideal sites. If your heating and cooling are right next to each other, this CapEx will be fairly low, much lower, I should say, than what we've shown here. So the business case would improve.
I think it's worth mentioning there, Charles. We've certainly seen cases where it's everything's coming together in a beautiful fashion for a heat pump, where you can see these cases where it's at the high fuel cost, gas price, a low electricity price. You know, the company doesn't need to upgrade electrical systems. They've also already got some thermal storage in place. The heat requirement, and they don't need to do much changes for the reticulation system as well. And quite often this all fits in together. And that's where that case where this cost here would be, you know, minus 20, even more from that CapEx estimate that you've got there. So we say it's conservative and you've got minus 20%. It genuinely can be at least minus 20% below this estimate as well. So it is conservative. Yep,
absolutely. And it's designed to take into account your the site's own data as well. So it is conservative in a way, but the savings are relevant to the site specifically. So it's only the CapEx that will skew the numbers a bit. So it's important to keep that in mind. So I'll do one more example. So here is a hotel, just a different setting. They've got a resistance hot water heater, a very old resistance hot water heater that's heating water to 65 degrees. Now we know straight away that's extremely inefficient, but they're a big user. Their annual heating cost for water is $95,000, and their marginal electricity costs are really cheap at 10 cents per kilowatt hour, which is why they haven't replaced the system after all this time. The average heating requirement is 200 kilowatts. That's the size of their hot water heaters. The site's in Melbourne, and the maintenance budget for this hot water system is $3,000 a year. But there's no uses for cooling whatsoever. Where the boiler's placed, they don't want to link it to the air conditioning system or any other cooling. So we'll have a look at what it means to do this. So let's enter the example. So here we've got the input fuel heating cost at dollars per gigajoule. So we've got to convert that from 10 cents per kilowatt hour to dollars per gigajoule. So I've done that legwork, and it's $27.80 per gigajoule. We've got annual heating budget, so the energy use of $95,000, and you'll see that this is blanked out. We only need one or the other. So if you know the operating hours of your process, you can put that in. If it's easier to put just the budget of your heating or how much it costs for you to pay for the energy for the heating, you can put that as well. We want to make it really accessible, this tool. The electricity cost is 0.1, 200 kilowatt heating. It's going to be an air source because there's no available cooling water. And you see a lot of these things black out because for an air source system, there is no cooling sides. We're sucking in ambient air and we're expelling cold air as a result. This is in Melbourne. So straight away, they'll take the average ambient air temperature of Melbourne for these calculations, and we want 65-degree water. The heating efficiency here, it's electric resistance, so it's 100%, and it's $3,000 is the operating cost. And again, you can see here what the numbers are telling us. For this one, it really is a no-brainer to replace this with a heat pump. Either ammonia or CO2 will work. We've got the COPs. There's no cooling COP, so that's why it's 0. We've also got the levelized cost of thermal energy delivered. So here for the heat pump, it's about 3 cents per kilowatt hour of thermal energy. Now we can calculate the levelized cost of thermal energy for the existing system, but we need the lifetime. So let's say the system was initially rated at 15 years when it was brand new. And it costs $8,000 or $80,000 to put in at the start. And we can straight away compare the different levelized cost of energies for the two different systems. So this advanced output feature is still needs a bit of work, because you can see here it's missing MPV. The idea is to continue working on this, continue to calibrate these data and these models to make it more accurate and refine it a bit more, and perhaps add a couple more parameters that people feel are relevant or important when considering this type of technology.
Charles, we've got plenty of questions coming through. I might just we might just go and answer a few of those, and we'll finish off the one that we had from Nikita on the aquatic centre. I think you showed a really good simulation quickly there on aquatic centre with the temperatures. That was great. One question that was also in there was the need to have backup power and backup security. And you may think, well, is that needed in those winter months? And you say, well, no. I mean, the heat pump is still going to work absolutely fine and down to those lower temperatures. Yes, the COP is going to be lower when at the lower ambient temperatures and what have you. But certainly the report that I'm seeing is it's certainly not needed for any sort of backup fuels, backup boilers, backup CHP, nothing like that at all, as long as you've got that consistent supply of electricity. That's how I've certainly seen the reports look. And I don't know if there's any comments there from the panel on that one.
Yeah, I agree with that. It's ultimately it's up to the site. If the site needs a backup regardless of what the technology is, then you'll need a backup regardless. A boiler, the way I see it, a boiler and a heat pump have similar performance reliability characteristics. If you maintain it well, then both technologies will provide similar levels of security in heating.
Again, when you look at those colder days of the year, certainly the heat pump still works fine. Even the lower temperatures where you may need some defrosting, that's going to impact your COP, but only for a few hours per year, not hundreds of hours per year. Good.
And those are the sort of things that if you live in an extreme environment, when I say extreme, it's extreme cold or extreme heat, it's a good idea to do a more detailed study before you jump into investing into this technology. This is a very early go, no go perhaps for yourselves that anyone can use, and it's designed to be very, very accessible. So as a result, accuracy has been sacrificed to an extent, but we'll go through some of the calibration that we did with projects that that had a detailed feasibility conducted, and I compared the numbers from those reports versus the outputs of this tool in a couple of slides, so we can go through what sort of accuracy we're looking at.
I've got a question here about the ongoing maintenance costs of heat pumps compared to traditional boilers, and the data that I've seen, it is less. You certainly do have to allow for a boiler, and if you're allowing for potentially a retubing or some major works to be done, and you factor that into the overall annual cost, then certainly I've seen that the lower costs for the heat pump. I'm not sure of the exact numbers, but all the reports that I've went through showed lower costs. Anyone in our panel's got something further to add on that one?
I think you have to be careful. You have to be careful with talking between commercial and industrial. So we have to now, at that point, consider the lifespan of the unit. For instance, a packaged air to water heat pump used in an aquatic centre might have a lifespan of sort of 10 or 12 years, whereas a reciprocating heat pump used in the centre might have a lifespan of 30 plus years. And then the maintenance, of course, in that air to water heat pump in the commercial side towards the end of its life goes through the roof. And if you've got multiples of those in the buildings, some of these aquatic centres we've seen have 8 heat pumps attached to them. So of course your maintenance bill towards the end of the life cycle of that equipment just goes off the chart. So it does have to be careful consideration of the lifespan of the existing building, the projected lifespan of a new building if you're building a new building, and really sort of take that to on advice, or good advice, before you invest the money in that. Again, heat pumps are not a magic bullet. They come with strings attached depending on the system you're putting in.
In terms of the maintenance network, though, it's typically going to be the current types that of industrial refrigeration contractors, which already have national networks. And of course, we're referring to companies like Gordon Brothers, Tritech, and Cold Logic on that sort of thing. So yeah, the networks are in place for that maintenance already. A good question here from Russell about would we be sharing the selection tool? Absolutely, that is the intention. Looking to have this one go live for you all, possibly in a web format towards the end of this month. So look out for that one.
Yep. And Jen's also asked, would the tool give an indication of the size of the thermal storage needed? Yes. That is not here at the moment. It's one of those advanced outputs where it does need a little bit more work to split out the capex and the sizing of the thermal storage, because it is a little bit more complicated when we're dealing with peak loads versus average. But yes, the intention is by the time that this tool goes live, you will have that.
And that thermal storage is typically just a sort of a rather vertical dimensioned tank, and certainly just the one single tank can be managing that thermal storage as well, as I understand, Charles.
Yes, because we're only dealing with sub 100 degrees water at the moment. Storage is just in a sensible thermal storage type. It's probably not going to be a phase change type thermal storage, which is a bit of an overkill for something like this. So again, those are the kinks that needs to be worked out once a little bit more work has gone into this tool.
Question here from Gabrielle, Gab, asking about the type of refrigerant. Anything other than 717, 744?
Right now, that's the only tool that we're considering, because we want to focus this on natural refrigerants. So those two are the most prevalent natural refrigerants that's commercially available. There are others that's coming into the market, like propane, isobutane, water, etc., but they're not yet commercialized. And the intent is for this tool to add those as they become available.
And whilst commercialised, we may say not commercialised in Australia. So there is the other refrigerants, the R1, 2, 3, 4, with the alphabet afterwards, that we could incorporate into this fairly easily. We took a cautious approach, considering there's some uncertainty of those refrigerants being available in sort of 10 years' time. But if that changes, I'm sure we can easily update it to add those refrigerants in as well. And I think certainly if we start looking at above 100 degrees, and we want to make this tool to look at above 100 degrees, we certainly would need to include the R1, 2, 3, 4s as well.
Just to clarify on that point, your refrigerator at home has butane in it currently. So that's a natural refrigerant we're not including. And the limiting factor with isobutane, butane, propane as refrigerants is they go bang very happily. So you're limited by the size of the charge in the unit. They're currently working on adding CO2 to these refrigerants and then working out a safer way to use them. But if you turned up to a large industrial site and said, I'll put a butane or a propane heat pump in here with 200 kilograms of charge, all good, but you'll probably level the building if it leaks. So there's a great danger in these refrigerants as they get bigger with their flammability and explosiveness. You still have flammability in ammonia, but it's very slow. Consider the width of your laptop, and the flame would move across that in about 2 or 3 seconds, compared to butane, which when you light a match, it will take out all the windows in the building. So a lot of people in Europe are saying that is the future, is these refrigerants are the future, but we just have to make them more palatable for bigger installations.
Good. We've got a question there for Patrick about regional areas of heat pumps would often be displaced LPG, and I think we've covered that one when we talked about the cost of just changing that dollars per gigajoule. I know that I think we've got 27.8. That sounds about right for volumes for LPG. So it looks like you've got that covered. So just a matter of making those adjustments, as Charles mentioned before.
Yep. And you can do not just LPG boilers, you can do any sort of boilers, biomass boilers, which all you do is change the efficiency. The biomass boilers are close to about 60% efficient. The cost of biomass is far lower, $8 per gigajoule, let's say, and the factors adjust for themselves, and you can change the temperatures and things as you see fit for your case.
Good. And Bruce and John, well done, thank you. I think they've resolved that question on the COP. Yes, we think a 50-degree lift around a COP of 3 or more certainly seems feasible. Claes, we've got a question there. If you use AC chilled water as a heat source, do you give a credit for the energy savings accrued to the reduced cooling capacity required from the AC chilled water system?
Yes, you're basically using this heat pump as a chiller on the cooling side. So this energy savings, when you take the, so if I change the heat source back to water, so if I'm cooling water from 20 degrees to 10 degrees, this is essentially a refrigeration system, and it takes into account the COP of the cooling side. You'll notice that this is far lower than a typical cooling system from ammonia, and that's because we're not just using the cooling, we're using the heating as the main form of application, and the cooling is just a benefit. So the cooling is a bit reduced, the COP that is, as a result. But yes, you essentially get free cooling by producing hot water.
Plenty of questions still coming in, which is great. Let's try and punch through them, Charles. Capital cost of PV solar in the total CapEx cost, is that included?
No, the capital cost of PV is included in the OpEx. We're using a levelized cost of energy approach for PV, which just changes the electricity cost. So we're not getting free electricity. We're getting electricity at about 6 cents, which is around the levelized cost of electricity from a solar PV. So we've skirted around that problem by just accounting for it in the cost per kilowatt hour figure. Hope that makes sense.
I think so. Question here from Johanny. We're talking about the, do you have to use renewable electricity? What have you? I mean, the tool, it doesn't mind if it's renewable or not. It's still workable for both. This should be an enabler to use renewable and PV. That's for sure, though.
Yep. It gives you the choice to actually look at whether it's worth powering the whole thing using renewables, or just use grid electricity. If you've got a cheap enough rate at the moment, you might not find the need to do that right now. So you can play around with this portion of energy use of heat pumps from solar, anywhere from 0 to 100, and that'll just produce a sensitivity analysis for yourself to see, well, what is the sweet spot? Should I power 10%, 20%, if such a sweet spot exists?
Good. And does the selection tool allow for using a variable speed drive for the heat pump, or is it constant speed?
We haven't got to that yet. So here we're assuming the heat pump is variable. The CapEx cost we've put in have accounted for a variable speed heat pump, but all of the energy calculations are assuming it's fixed speed. So that's the sort of compromise that we've done here.
And in terms of the electricity cost, we don't have anything there for time of use tariffs. It's not that smart, the tool, yet. So I guess that's something that you'd have to play around and simulate a few different scenarios to do that yourself for the moment.
Correct. Yes, because the heat pump can operate at any time, or we haven't asked for the time of use of the heat pump. It's very hard to incorporate time of use electricity. So we need to do both or neither, which is what we've chosen here.
Good feedback. Thanks, Graham. And I think that if you've got to that level of detail, that's when it's time to call up your energy consultant, like a pitt&sherry, Northmore Gordon, 2XE, Energetics, Dita, these sorts of guys, SmartConsult. You've got Regenerative. These guys will certainly help you take that further. Good. Okay, maximum heat out temperature from Scott.
Yes, there is. Right now, it's capped at, so if you put in 90 degrees, it won't work. It's capped at 85 degrees. Now, we are looking to expand that cap because we do have a little bit more data now on about the 90 and 95 degrees. So by the time this tool goes live, I expect it to be at least 90 degrees. And then in the future, once steam replacement versions of these heat pumps become available, again, that gets stretched out a little more. But at the moment, it's at 85.
Good. And we've got the local suppliers like Glacium. I think we'll get some double checks on this to make sure that's matching what their product range. And there's a question there coming in from our mate about the size of them. We'll do plenty of double checks to make sure that works. And obviously the likes of Mayekawa checking with them as well. Good. Richard, you've got a client that needs chilled water applications, also has significant 75-degree hot water demands. Should a heat pump be considered? 75 sounds well and truly doable for a heat pump. That sounds like an ammonia ammonia job. If you need more chilled water, I guess that heads it more towards a decision of it could go either way between ammonia and CO2. Charles, what's
Yeah, absolutely. So it just depends on what you need. If you need a lot of cooling and heating, CO2 is probably your best bet. If you need a lot more heating than you do the cooling, ammonia is probably the least cost option for you. And again, this tool, once you have the data of your energy costs, you've already got the temperatures that you need, put that in there and see what it does. It should give you an outcome pretty quickly.
And from Timothy here, for the tool and more generally, where both heating and cooling are used, is there an implicit assumption that thermal storage would be employed for both heating and cooling?
Yes, that is the case. So we haven't made the distinction that it needs to be used simultaneously, both the heating and cooling. So the CapEx costs that we've put in there does include implicit thermal storage for both sides. And again, we are working on separating that out so that you do have thermal storage on the heating at the very least. Thermal storage on the cooling might be a bit trickier to work out. It does require a few more inputs. So we'll put that as a good to have, but it might not be able to put this into the final version of this tool at this stage.
That's certainly the case where that heating and that cooling often don't match. So it could well be required to do both for sure. Have you got the total annual kilowatt hours used by the system? Is that there, or the kilowatt load at least? Where do we have that one in there, Charles?
It's not shown, but yes, it's there. So it's one of the calculation outputs that I've hidden in here. So I can make that visible. That's no problems at all.
There from Brendan saying that, you know, if you look at this hotel example and you consider Melbourne, an average temperature may not be that useful. Can the model have high and low air temperatures instead?
Yes, it can. So it does require a bit of work to change it a little bit. So what we're doing now, the approach we're taking is that use an average temperature to get the average COP over the course of the years, but then have talking points and give you like a range of maximum and minimum COPs depending on what your location is. So it might be that the average COP is 3, but it will not work during a cold day for that particular area. And it'll tell you that this is a possible risk. You should look a little bit more before jumping into this.
Yeah. Good one. Thanks, Brendan. Scott, another one there. Would be good to have a manual override for ambient air temperatures rather than just a drop down of locations. You can do that then, Charles?
Yeah, I can do that.
Yeah, great. Thanks,
Let me
Scott.
just note that down.
Yeah, Glenn, he says Europe heat pumps are rated down to -20. So, you know, using a heat pump to low temperatures, not an issue at all. That's certainly almost like the home of heat pumps right now is Europe and Japan. So yeah, much colder climates than what we have. From Ben, would be worth considering redundancy in your selection and capital cost pricing? A standby heat pump versus standby boiler may extend your payback. And I think that would come down to, you know, you'd take a similar position to what you do with your chiller system. You know, similar availability there. I don't see, that's not always the case, having that backup for a complete backup chiller system. But if it's that sort of reliability needed, that may be there. But I'm not sure there's such a big difference if you're doing proper maintenance there.
Yeah, and you can do, I mean, like the refrigeration side, an N+1 configuration is, if that's what you need, then that's what you should get. And in this tool, the way you would account for that is doubling the capacity, but keeping the total energy use the same. So you would keep the same heating budget, but you would put in a much larger system to account for the fact that you need to have an N+1 configuration.
We're talking about from Dipanshu about the industries is using water-to-water heat pumps in Australia, and which is better, air-to-water or water-to-water. I think when we talk about the efficiency of the heat pump, water-to-water, definitely every time. So if you can find that heat source, whether that be wastewater, sewage water, or something like that, definitely the way to go. But air-to-water, yeah, that's probably your second option if you don't have that heat source, Charles.
Absolutely. The preference is definitely water-to-water or groundwater to water. because it also gives you that opportunity to use it for cooling as well. If you're using air, the air is exhausted as cold air. Now that might be useful for your sites, but it rarely is for most places. So you're losing half the performance of the heat pump straight away.
We talk about the suppliers of industrial heat pumps. We'll cover that in the final version of the selection guide, and we'll make that as part of the program as well. Obvious one being a sponsor of sort of the guide themselves is Mayekawa, and the likes of Glacium doing the CO2 ones. There's a pretty obvious two there, but there is several more. There is a lot more that are present in Australia as well, and it seems to be building up, which is good. So that makes it certainly nice and competitive. Okay, almost there. Is it possible to achieve 70-degree temperature by using reversible heat pumps? I mean, 70 degrees, yes, no problems there at all. Not quite sure what a reversible heat pump is. The assumptions behind the cost data, will that be made available? Don, I'm not sure. Everything will be completely open and transparent, but we'll certainly try and give a list of the assumptions and how we've come to these calculations, that's for sure. There we go. Charles, well done.
Excellent.
We got through. Okay, we're nicely ahead of schedule. So with that, I might just take back the presentation there, Charles.
Yep, no problems. Let me just stop sharing.
Good.
Oh, there's a couple more things I wanted to quickly go touch on. Jared, do you mind if I grab that back? Apologies. There's just a couple points about the accuracy of the tool that I want to quickly elaborate on. Sure. Let me just... There we go. Okay, so we've ran the tool using the parameters that we have from previous feasibility studies. So these are feasibility studies that have been done and are available on the A2EP website as separate case studies that you can have a look at for more information. So in this case, it's Lions Brewery in Adelaide, where we looked at the feasibility of a carbon dioxide heat pump system to produce CIP water. And in the report and through the detailed feasibility, which cost a fair bit, we came to a 4.4 year payback at around $200,000 in annual savings and $960,000 in CapEx. The tool, which I put in the figures in less than 2 minutes, provided very similar outcomes. Now, the CapEx is a little bit low, the savings a little bit high, and the payback is a bit on the low side. But as a 5-minute replacement to a 3-week long project, that's not bad, I feel. And then we also ran some sanity checks using a separate project. And this one is for Simplot, again, another one that A2EP has done recently. And again, available on the website as a separate case study if you want a bit more. But this one is an ammonia system, which takes heat from the existing ammonia compressor discharge lines and cools that for additional heat for production of 75-degree hot water. So in here, we found in the report and the tool line up fairly closely, and it's well within that error tolerance that we said previously. And the payback is very similar. So again, a rough sense check from the real projects indicates that this tool is relatively accurate. The engineer in me is saying that this is not good enough, but the project manager in me is saying that this is all right. So we might leave it at that.
Well done. Thanks, Charles.
No worries.
And those paybacks you were showing there were really just on the energy benefits alone. Wasn't allowing for sunk cost in a boiler, wasn't allowing for the value of increased production, and a lot of other things as well. So that was a simple energy payback. And what we see time and time again is that when you look at the non-energy benefits, that's when the projects go ahead, and you see the paybacks and the return on investment really skyrocket after that. Very good. And just to round things off then, and just to remind you all of what is available, the resources that are available. So if you go to a2ep.org.au, you'll see that our past the past presentations and webinars on heat pumps are there. The one we have with Corden, great presentation, as well as we had Alliance from New Zealand and ECA from New Zealand presenting on that one. And then if you go to our work and publications, you'll see a lot of resources there for you as well. When we talk about heat pumps, high temperature heat pumps in the food industry, and we've also got some others there on replacing steam with electric technologies as well. So lots of resources there for you. For what's coming up with A2EP, we've got the Innovation Network meeting next Thursday. We're talking about metering and measurement. We've got companies of Schneider Electric telling us about their latest advancements to make it easier for you to meter and measure your energy data, along with Symbol. We've got Northmore Gordon giving us some examples, and some companies working on machine learning and AI to handle your energy data as well. So great webinar coming up for you next Thursday. Welcome you to join us on that one. Coming up in November, from the 9th to 12th of November, we've got our annual Innovation Exchange. And here we're really talking about helping you make energy productivity in action. Helping businesses to understand what it takes to get to net zero, understanding strategic investments. We'll also take a look at the low-hanging fruit, the absolute sort of no-brainers for energy productivity investments. And also we'll have the likes of many government departments join us and tell us about their latest programs, whether that be Sustainability Victoria. They've got a great tool to help you select what grants and things are available. DPI New South Wales, plenty of governments there wanting to tell you all about how they're making it easy for you for these sorts of investments. So that's coming up for the 9th to the 12th of November. We're also doing a webinar series for regional councils to let them know about how they can reduce the energy for their #1 energy consumer at all local councils, and that's their aquatic centres. So we're doing a webinar series starting off with Sydney regional councils, with Regional Development Australia and LG Pro helping us with that one, and that will be on the 17th of November. That is a closed session, but just letting you know there's more and more happening there with heat pumps. So with that, I think we're pretty well close to time for finishing. Let me offer the thank you and appreciation to our panelists today. Peter from Marina, thanks very much for joining us, and Rob, thanks for the introduction and starting us off there. To the team working on this tool, may I say, I think you've done a great job, and in a very short period this has been put together. So for Charles, Derek and Manuel, congratulations. I mean, we've got some great feedback there today, and I think we can just take that to another level before the whole guide is ready to be launched at the end of this month. So thank you for the work you've done. Thank you to everyone and their questions today. Really appreciated. And if I just have a really quick check on our Q&A. No, just positive feedback there for your team on the Q&A to finish off with. So well done. So with that, I'd like to close the meeting, and thank you all for participating, and hope to see you all next week when we talk about measuring and monitoring of energy. Otherwise, thank you and have a nice afternoon.